Okay, so good afternoon. Welcome to lecture 8. This is going to be continuing on op-amps and non-ideal op-amps, and in particular we'll be looking at limiting finite resistances, that means input and output resistances, and slew rate, things that you would have to pay attention to if you have a circuit using an ideal op-amp. But before going into this, as usual, some announcements. So homework number 3 is online. It's due this Friday via Gradescope. Your lab number 1 pre-lab is due before lab session. I guess there's a few people that have already turned that in then. Most of you, now regarding the lab number 1 experimental part, this has been online and most of you have your lab kits, so you should start lab number 1 this week. And the way that I think these labs are happening is that you're actually showing up to the Zoom lab meeting. Your TA is saying a few things about the lab, maybe showing you some things, and then in that period, the TA sticks around and can be help for you. You're all basically working from home anyway, so you're hooking things up and hopefully trying to take advantage of the fact that your TA is there to help you with any issues you might have in this. And so you should start your lab number 1 this week, provided you have your lab kits, and I think most of you have that by now. You would normally turn in lab number 1 at the next lab session, but this time, because there's variance in who has lab kits and who doesn't, we're going to give you 2 lab sessions to do this. And so by 2 lab sessions, what it means is that you just turn your pre-lab in today for the Monday lab people. Next week on Monday, usually what happens is your lab is due, the experimental lab part, and answering the questions associated with the experimental lab. However, instead of next week Monday, the lab number 1 experimental portion will be due 2 weeks from now, Monday. Okay? And so lab number 2, so this is where it gets a little bit tricky. Lab number 2 is already online. And so that lab number 2 pre-lab is going to be due next week in your lab. So if you're a Monday lab sessioner, lab number 2 pre-lab will be due at the start of the lab session next week. And that'll be the only thing that's due because your lab number 1 won't be due till the week after. And then lab number 2, the experimental part, which hopefully you'll be doing next week. Maybe you'll still be doing parts of lab 1 if you have not received your kit by now. Then lab number 2 would be due in 2 lab sessions from the date that the lab 2 pre-lab is due. Hopefully that's not too confusing for you, but I should also say that I updated the course schedule online as well. So if you go to this, you'll see these things here as well. So lab number 1 is right here. I guess it won't say when it's due. This is when the pre-lab is due. So when you see a lab come up here, that's the day that the pre-lab is due. And so normally lab 1 experimental session will be due here, but we're going to make it due here on the 28th. And then next week you'll come in for lab number 2. The lab number 2 pre-lab is due here, but the actual lab number 2 experimental portion write-up is not due till out here when you start lab number 3, and that's October 5th. Okay, so hopefully that makes sense for everyone. If not, I'm sure your TAs will be describing this to you in great detail when you get to your lab session. Let's see, Friday 9/18, that means this coming Friday lecture, it's again going to be a 12 noon lecture because I have, again, this meeting that is meeting right on top of our usual 2 to 3 p.m. I will again be recording that lecture, so hopefully that's not a problem because you can just watch the recording. Last time we had some issues with sound. Any issues right now? Okay. So I tried using a fan. Tested it on your GSIs. They didn't like it because they could hear the fan. But what I did was I found out that my computer was not running at maximum performance. So now I have it on maximum performance. If the problem is the heating, we're going to run into that again. But let's see. So, so if you hear sound problems, please let me know by chat or something like that. So that I know that I have to continue to try to fix it. Any questions about any logistics in the class at this point? I assume pretty much all of you have your lab kits by now. There may be some stragglers. All right, so the lecture topics today, we're going to keep looking at closed loop amplifier frequency response, but we're going to also go into slew rate and a bunch of other things as well. And so I actually needed to update this, and I guess I didn't, so I'll fix that a little later on. But right now, let's get to where we were before. So just a little bit of last week. So last week on Friday, we looked at finite op amp and finite gain and bandwidth here. And if this is the open loop response, we did an analysis for a non-inverting amplifier with this op amp that had finite gain, really more finite bandwidth, because we eventually assumed the gain was large enough that we can kind of approximate it as infinite. And we ended up with a situation where if you had that kind of thing, then what happens is, yeah, your gain goes down, but your bandwidth, which is, I'm sort of equating to the 3 dB frequency of the Bode plot, or the frequency response for the amplifier, that bandwidth now goes up by the amount that the gain went down. And so there's a gain bandwidth product that stays constant. Right? Whatever the gain bandwidth product was of the op amp alone, which I call the open loop op amp. Open loop means I didn't put any feedback around it. And then I compare that gain bandwidth product with the closed loop op amp, where I put feedback around it to close the loop that changed the gain, but it did it in such a way that the bandwidth went up by the amount that the gain went down. Okay, so that was one of the more important things we took away from last time. And so the last thing that we did last time was another example. I did an example of a non-inverting amplifier. Now what I want to do is an example of an inverting amplifier. And so this is what we did. This was the last thing that we did last time. So inverting amplifier example, you can recognize this inverting amplifier. Like last time, I wanted to do this with the intuitive approach. And so with this intuitive approach, what I'm trying to do is take the circuit and equate it to something that I know to some extent, and I think you've seen before, that's a system block diagram of a feedback circuit. And so we analyzed this last time as well in case you had not seen it. This is different from the non-inverting amplifier because I've got this resistor going from the input to the negative node, negative terminal of this op amp, which I call the summing terminal here, because what it does is it sums currents going through R1 and R2. We talked about that at the very end of the lecture last time. And so that's why, because there's some summation of currents here in the block diagram, I'm calling this a summer, and both of these are coming in with pluses here. And the negative feedback is coming from the actual minus terminal of the amplifier here. And so if you go around the loop of this, you'll see that this is indeed negative feedback. We did this in a previous lecture, so I won't do it again. But this indeed is negative feedback. And so the minus sign here, if I go around the loop and that's minus, that tells me I've got negative feedback. Okay, but this alpha here, which is sort of the transfer function going from the input to this minus terminal, which has to go through R1, that's now a new thing for us. And so if I want to analyze this in that intuitive way, where I'm basically going to remember what the transfer function is for this block diagram, then all I need to do is determine what alpha and beta are, because I already know what A of S is. I know that that's my op amp, and we have given a transfer function for A of S. So let's go ahead and do the things that we need to do. Determine alpha, determine beta. And here we go. Let's get alpha first. Okay, and so how do I go about determining alpha? This is where the art comes into this. Okay, so you're going to see this one time, and it may be a little confusing for you. You may need to go back and watch this lecture again. Really, practice makes perfect is what happens in this instance. So this is going to be one example. You'll understand a good portion of it, but you need to practice it, say in homework assignments or so, to really understand how to do this and to get used to it. So the first thing I want to do is I want to break this loop. So I'm looking for alpha, which is this sort of feed forward term up here. So I want to know what the transfer function is going from VI to V minus right here. And to do this, I have this R2 in feedback. The way that you do this, and I'm just going to tell you that you have to do this, really in 140 you learn the reasons why you can do this. But I'm going to ground out this R2 here in trying to determine this forward transfer function. You can think that makes some sense because in an ideal op amp, Usually you have a very small resistor at the output, and that's going to ground if you have no voltage going through this thing. Okay, that's just sort of a hand-waving argument I'll give you right now. 140 will teach you much more about why this is. And if 140 doesn't, then 240B will. Sometimes 140 doesn't get to it, actually. But right now, the procedure is 1, ground the output. Okay, and break the loop. Okay, and then feed forward. So feed the input voltage forward to get the needed transfer function from VI to the minus terminal. So let me just do that right now. If this is VI, I look at my circuit up above. VI, of course, goes into resistor R1. R1 goes into V minus, right? And this is where the op-amp is. Let's draw a dotted op-amp. This is where it was. That was the minus terminal of the op-amp. This was the plus terminal. Okay, but the real circuit that I'm interested in is not the op-amp. I'm interested in the resistors going across this. And so I have this resistor here that was R2, and I'm now grounding this. This is the circuit that now determines my feed-forward transfer function, alpha. And so now I can write V minus over VI, which is that transfer function. That is equal to alpha. And that is equal to, this is just a voltage divider. By inspection, you can just say that's R2 over R1 plus R2. Okay, so I now have alpha, which is this very term up in my transfer function up above, and so I'll explicitly say this is that alpha. Okay, and I'm doing this by looking at the feedback path there and breaking it open, in this case the feed forward path. So now what I want to do is I want to determine beta. Let me go to the other side here. Okay, this thing doesn't want to let me touch this. All right, use my mouse. All right, so on this side, let's determine beta. Similar procedure here, except this time I want to go backwards. Right, beta is in feedback, and so I'm going from V out. I'm on the right side now. I'm going from V out back to this node here as well. And so to determine beta, I want to now ground the input. And break the loop, or open the loop. Okay, and then I want to feed back my output voltage, V0, to get the needed transfer function. And pictorially, what this is going to look like is this. So here's my op-amp, which I don't want to consider here, but I at least want to show you where things are in this whole picture. And so the output now, I'm just going to drive with V0. And that's resistor R2. I have a resistor R1, which used to have an input here, but I'm going to ground that now. So it's kind of like determining an output resistance, but not really. In this time, we're determining a transfer function. This node right here is V minus, of course. And so my transfer function is going to be V minus over V out as a function of S. This is beta. And so that is just a voltage divider again. That's just R1 over R1 plus R2. And so that now is my transfer function beta. And so I'll go all the way here and I'll say that's that. Okay, and so now I have alpha and beta. But if I look at my block diagram, which I'll bring into the picture again on the left, this block diagram at the very top, this is not something we have played around with before. You may have in a previous course, but in this class not yet. So I'm going to go ahead and determine its transfer function. Okay, so now let me get the transfer function for the system block diagram. And so let's start with that. So I'm going to use this block diagram to the left. It's a little bit small, but I think you can all see it there. So the first thing I'm going to do is write an expression for V0 based on what's going into this. So in V0, this is basically going to be whatever's going into my amplifier times minus AS. And whatever's going into my amplifier, oops, let me make that blue here. Let's call there our error voltage like we did before. And so in this case, V0 is going to be minus A of S times whatever that error voltage is. Okay, and I know that that error voltage is just what happens through that summer there. So it's going to be equal to alpha times VI plus beta times V0. Okay, I can go ahead and plug in VE into this equation, so plug this into there. And if I do that, I'm going to get V0 is equal to minus alpha times A of S times VI minus beta times A of S times V0, where I've skipped a few steps knowing that the voltage coming in this direction here is just V0 times beta there. And then I can do a little bit of rearrangement. So V0 times 1 plus beta times A of S is going to be equal to minus alpha times A of S times VI. And then finally I can write that V0 over VI as a function of S is just going to be equal to minus alpha times A of S divided by 1 plus beta times A of S. So that's the transfer function for this system block diagram. Anytime you see this system block diagram, this is what its transfer function is going to be. And of course, at this point I know what A of S is, so let me substitute that in. I know that A of S is my op-amp transfer function. That's A0, its sort of DC gain, divided by 1 over S omega B, which is its frequency shaping term. And so if I go ahead and plug that in to the above, I end up with V out over VI as a function of S is equal to minus alpha times A0 over 1 plus S over omega B divided by 1 plus beta times A0. Let me make this look like a knot. Okay. Divided by 1 plus beta, 1 plus S over omega B. And then finally, if I rearrange with some algebra, this will reduce to V0 over VI as a function of S is equal to, and just pulling out my gain term, minus alpha A0 divided by 1 plus beta times A0 times my frequency shaping term, 1 over 1 plus S over omega B times 1 plus beta A0. And so with this, you're seeing similar things to what we saw before. So I'll put this in a big square because that's our final solution here. This is for our inverting amplifier. And you see that it's different than what we had with our non-inverting amplifier. And the main difference is this alpha term here. Okay, so in fact, I can put down a few remarks for this. And because I don't want to spend time writing, I've sort of prepared these remarks. I'm just going to grab them here. Oops. Let me grab these remarks and just stick them right here. and then let's look at them. Okay, so what I just said, the closed loop gain is now modified by this alpha, right? Everything else you see here is the same equation that we had for the non-inverting amplifier. The only difference is now we've got this alpha and we've got this minus sign there. The bandwidth in particular is still omega b times 1 plus beta times A naught. So what you're saying is that we applied feedback around this to get a different gain, and you know what that gain is. I guess I'm not plugging in values for this because on your homework you have this exact same problem, and so I'll let you plug in the values to actually get the actual transfer function here. But I do want to look at this form right here. Right? So our bandwidth is widened. It's bigger, omega b times 1 plus beta A naught. I see that b doesn't look like a b, so I'm going to make it look like a b. There it is. And that means that my omega t looks like it could still be the same, but it actually is not. Right? My bandwidth may be bigger and the same as what it is for my non-inverting amplifier, but now the omega t, or gain bandwidth product, is smaller than that of the open loop amplifier because our gain is smaller. Our gain is now modified by this alpha, and remember this alpha here, because it's a voltage divider, here it is right here on the left side, that's going to be less than 1. So let me write that down. This alpha is less than 1. So in fact, this inverting amplifier is going to have a smaller gain than my non-inverting amplifier, and that means its gain bandwidth product, alpha times omega t, is going to be smaller. Okay, so I just said a few things in words. I did the equation. I said them in words. Now let's really bring this home by actually plotting this. By actually going back to the original plot that I had, and let's now plot our inverting amplifier on this same plot where we have the non-inverting amplifier and the open loop op amp here. Okay, so for my inverting amplifier, remember what I just said. I said that it has the same bandwidth. So the inverting amplifier bandwidth will still be omega b times 1 plus T naught. Well, remember, T naught is equal to beta times A naught from before. So let me write that down. It's the same equation, but I'll put it in red. Omega b 1 plus T naught. Okay? So I know that that's my 3D bandwidth for my inverting amplifier. The difference now, though, is that the gain of my inverting amplifier is equal to the gain of the non-inverting amplifier but multiplied by alpha, and alpha is less than 1. So if alpha is less than 1, then my gain is going to be smaller. And my gain is going to be smaller, something like this, by an amount equal to the dB of that alpha term there. Right? So that's going to be smaller there. And if I'm just doing magnitudes here, that's going to be 20 times the log of 1 over alpha, that distance between the green dotted line and the red dotted line. And so when I want to plot the Bode plot for the inverting amplifier, it's going to look like this. And then it's going to hit right here. And the asymptote going down is going to be here for my inverting amplifier. And what you're seeing here is that its asymptote, the whole curve, is now below the green curve, which was the curve for the non-inverting amplifier. Okay, so the red curve that I have right here is this same op amp, the same op amp in blue that I'm showing here, except now with non-inverting amplifier resistors, same resistors as I use for the inverting amplifier. But when I have inverting amplifier feedback, I get the red curve when I close the loop. So this is an example of another closed loop transfer function. I've closed that loop, but now I have less gain and I have a smaller 3 dB bandwidth. Okay, that means my gain bandwidth product is smaller than it was for the non-inverting case and for the op amp itself. Right? This is now the omega t for the inverting amplifier case. And so what does this tell you? It says that the non-inverting amplifier, if you just wanted sheer gain, bandwidth performance, non-inverting amplifier is the better way to go. Okay, inverting amplifier is not as good an amplifier as a non-inverting amplifier. And we've just proven that with just this understanding, this sort of brute force and intuitive analysis of the feedback circuit. The question here, is a smaller gain bandwidth product a sign of some kind of energy loss through this circuit? Yes, it is. So just putting the resistor up front, that resistor R1, actually impacts a few things for you. You already see how it impacts because it creates that alpha term here. But in the end, when you make an inverting amplifier like this, what you're really creating is an amplifier that really wants to amplify current to voltage. So the input it really wants is a current into the minus terminal. And in this case, we're giving it that current by sticking a resistor here, and VI is being divided by that resistor. We have to create that current through this resistor. If we just had a current going straight in, this amplifier would love that. Okay, but this is still a very useful amplifier, right? Nevertheless, because it inverts, whereas the non-inverting amplifier doesn't. And a lot of times we need that inversion, and a lot of times we want that inversion, and we care more about that than just this little reduction in our gain bandwidth product. So still a very useful amplifier, one of the most used amplifiers around. The other nice thing about the inverting amplifier is you really have this virtual ground at this minus terminal, so you can knock out a lot of capacitance for that device. So some of the stuff that I talked about where I said this is really a current amplifier, that's stuff that you learn more in 140 when you really delve deeply in the feedback. So don't worry if you didn't quite understand all of that there. And I'm not going to go into great detail on that here because you should wait for 140 for that. What kind of situation will one use an inverting amplifier over a non-inverting amplifier for an 8? Well, I just said a situation where you want the inversion. It is really as simple as that. Sometimes you just need that inversion. Say you have something where you have something that's already amplifying in a positive way, but you want a differential signal, so you need to create a negative. You can do that with this inverting amplifier. Okay? Okay, so that's gain bandwidth, and I think I'm finished with that topic right now. You have some homework problems on that, of course, and one of them very similar to the one that I just did. But you'll also have to apply SPICE to that too. Definitely go to your discussion sessions this week. If you have not used SPICE before to simulate, because you're going to need to do some SPICE this time around. That's in preparation for your lab, where you need to do that too, lab number 2. But let's move on now to talk about other non-idealities of op-amps. And the next one I want to talk about here is output saturation. This is something actually that we have looked at before in the more general context of a general amplifier, not just an op-amp. But an op-amp is an amplifier, so of course you would expect it to have a point where its output saturates. And for this, I'm going to bring in a nice transfer function that I have for an op-amp, and this is going to look a lot like what we did before, but I'll do it nevertheless. There's my op-amp transfer function. And when I talk about op-amp saturation, what I mean is that there are limits to how much voltage an op-amp can put out. And so in this case, I have V out versus VI, and let me show you what I mean by that by drawing the op-amp. Okay, so if this is the plus terminal, that's the minus terminal. Then VI I can specify as this. This is my output voltage. Of course, you know that's going to be equal to some kind of gain. In this case, I'm ignoring frequency effects, so I'll just call that A0 times V plus minus V minus here. Which is my input there. That's VI. And so if I plot everything on this plot here, what happens is that this op-amp really has a supply rail, right? I'll call this L plus and L minus. I'm using L for limit. And so on this plot here, I could say this is my limit. Say that's L plus, and at the bottom, this is L minus. And this op-amp cannot put out any voltages greater than L plus and L minus. And so it all depends on how big your input signal is. And so I'm going to do the same thing that I did with that other discussion. I'm going to go ahead and stick an input signal. And first I'm going to make an input axis in blue here, where that's time. Okay. And then in this direction is going to be my amplitude. So that's VI, my amplitude. Let's say I have an amplitude this big. that I'm putting in to my VI. Well, let's first put a reasonable amplitude in. Okay, so if I put a reasonable amplitude, and usually that VI is going to be very small because feedback will ensure that it is. And so if this is my VI, just that big, then I can draw in its sinusoid as this. Well, let me draw the sinusoid down here so it doesn't disturb that curve. Let me pull this out a little further. That's time. And let me make my VI axis here instead. So that means I'm putting in a sinusoid that looks like this between that. And if I do that, then I project it up to this this curve. You know already, because I've done this before, that I can do this. And if this is now my output voltage, let me make that much bigger here. If this is my V out, and I'm creating a time axis here, then I've taken this tiny input signal and I made it bigger. And so you can sort of see how this amplification occurs just because I've got a large slope, gain slope right here. So this slope is that gain A0. Okay? And so what happens if I put a much larger signal through this? So I try to put in a much larger input signal here. So say I go here. Let me try to do the same on the other side. So say instead I put this signal in. To my input. Now I'm going to project it to my output here. That'll go up there, and you can see this one sort of hitting there. But the thing is, I cannot output a signal this big, where the dotted line is going across here. I cannot output a signal. I can only output a signal as big as L plus and L minus on the negative rail. And so effectively, what's going to happen is my output's going to go up, and then it's going to rail out and flatten. And it's going to go back down. It's going to rail out and flatten, etc. In the end, it's going to look almost like a square wave coming out of this. And that's happening because I have a limited output range, and that's output saturation. Okay, so at this location right here, the op-amp output limits or saturates. Okay, and so that's just one of the non-idealities, very practical one that you're bound to see in lab. I'm pretty sure you're going to run into this in the lab when you do this. Okay, so we covered that before. I'm not going to belabor that. I'll leave it on the screen here. But let's go on to cover some more op-amp non-idealities. And the next one I want to cover is slew rate. Well, no, first let's do finite input and output resistance. That's something you've sort of seen before, but let's make sure we cover it in detail here. And I'm actually going to also show something that you're going to need to use in your homework assignment, especially when you do SPICE. So you know already that all amplifiers, all practical amplifiers, will have a practical finite input and output resistance. The op-amp, if it's ideal, would love to have an infinite resistance and a zero output resistance, but in reality you don't get that. So if I were to really draw my op-amp model, I would have to draw something like this. Okay, so I'm going to draw a big op-amp here, basically. And so here's one terminal going in. Maybe that's my minus terminal. That's going in now. Instead of to an open circuit, that's going into a finite resistor. And that's my resistance Ri. Let's call that V plus there. I then have in my op-amp, if I wanted to create an equivalent circuit for it, I would put a voltage-controlled voltage source here that would have a value A sub v times v plus minus v minus. Okay, and then I would have an output resistance, so I'll call R naught, and this actually is what is internal to my op-amp. So I'm going to draw basically the triangle symbol of my op-amp here. You can see what I'm getting at here. That then becomes the output for my op-amp. And so this is sort of the circuit that I need to use. Right, this is the minus terminal, the plus terminal of my op-amp here, but this is the overall circuit that my op-amp really is. And so when you're simulating an op-amp, and you know its gain, A sub v here, and you also know its input and output resistance, this is the circuit you simulate. Never mind the big triangle outside. This is the circuit you want to simulate. So for that problem on your homework, this is what you want to build in SPICE. When you simulate an actual op-amp that you're going to put feedback around. Okay, and I'll let you go ahead and put those elements together. And I should also say that, you know, if I really want to make this a non-ideal op-amp, so if it's a non-ideal op-amp, you know that its actual transfer function is going to look like this. So if this is log omega, and this is A sub v of j omega, then this is going to look like this. Now you already know that the transfer function looks like this, and you already know that it's going to start going down at 20 dB per decade, starting at frequency, radian frequency omega b. You know that its gain is going to be whatever the gain was that we said it was before, A naught there. So you know that's its transfer function here. But this circuit that I'm showing right now does not reflect this transfer function because somehow I have to stick this omega b in. I have to stick the pole in. Okay? The best way to stick the pole in an ideal op-amp type circuit is just to stick a capacitor in a certain spot. And where I like to stick the capacitor is right here. I'll just put a C naught capacitor there where I will choose C naught such that omega b is going to be equal to 1 over R naught times C naught, and that then creates that pole. Okay, so if you want to model an op-amp, this is a great way to do it. You first determine its input resistance, its output resistance, its gain, and if you know it's 3 dB cutoff, just stick a big capacitor out here that works with that R naught that creates that cutoff, and that then becomes our op-amp equivalent circuit. This is what you would do in SPICE. Now, if you knew more about op-amps and what happens inside of them, something that we're going to learn hopefully by the end of this class, then you'll see that the innards of this op-amp look quite different. Right? The innards of this op-amp actually look something more like this. And so on and so forth. You've got a bunch of transistors. And I'm actually taking the time to put the whole op-amp down. Even a capacitor in there. This is what inside that. Okay? And so in this course, you will learn about these things. These are MOS transistors that I'm drawing right here. And we could also make this in bipolar transistors. You'll learn some of the structure here. Maybe not all of it, depends on how far we get there, but at least this structure, some of this structure there, you will learn. And this is what's actually inside these op-amps. This is the magic that happens there. And because these are real devices, you can never get Ri to be infinity. You can never get R naught to be 0. You can never get gain to be infinity, but you can get close with these types of devices here, these transistors. Okay, but for right now, the main point is when you want to simulate an op-amp, this is your equivalent circuit right here. Okay, and so now let's move on to talk about yet another non-ideality of op-amps, and that is slew rate. Also something that you're going to want to know for this homework that's coming up. The very last few problems deal with slew rate. So what is slew rate? To do this, let me just take an example. Let me take a unity gain follower circuit that uses an op-amp. And if you don't know what this is, I'm going to draw it for you. Hopefully you've seen this before. This is just an op-amp buffer. And so here's my op-amp, plus terminal, minus terminal. I'm coming in with an input right here. And all I'm going to do is tie my negative terminal to my output. And if I do this, I'm going to get basically a gain of 1 across this. That's why it's called unity gain. But it's a buffer because what it does is it makes my input resistance look enormous and my output resistance look very small while still keeping a gain of 1. And so there's a lot of reasons why I want something like that. Let me make this look a little nicer here. Okay. And so for this, when I take the op-amp, of course, it's going to have some gain function to it. Right, so this op-amp actually is going to have a gain function that, let me just make sure I have enough space. Well, I'll draw the gain function again for an op-amp. It's basically this. Right, where I have this omega B, and this is my omega T right there. And the original op-amp gain is A0. It's my A of J omega. That's my log omega. And so when I close this feedback, what happens to this? It goes to unity gain. And so if this is in a dB scale, then, well sorry, I guess if it's in a dB scale, then that's 20 log 1. This is 20 log A0 there. And so 20 log 1 is 0 dB right there, but that's unity gain, right? And so if I put this feedback around this op-amp, what did we learn happens to that? If I wanted to draw the new transfer function, and I'm showing you exactly how you should be doing this, how you should be thinking about this, all I have to do is take the new gain, which is 1, it's unity now, stretch it across, wait till it intersects the open loop response, and then there you go. Okay, so the black line, that's the open loop op-amp response. The red line is the response for when I put unity gain feedback around it exactly using that circuit. Okay? And so you can see that my new pole frequency for the unity gain is omega T. So that means if I wanted to write out the transfer function for this op-amp circuit here, the unity gain follower, it'll be V0 over Vi as a function of S is just my gain, which is 1. Divided by 1 plus S over my 3 dB bandwidth, which is now my omega T. Okay? And so you've dealt with responses like this before in the 16s. Now, this is the frequency domain plot or the phasor type plot. You've converted this to time domain plots, and you can do that by solving the differential equation, or if you know Laplace transforms, that's a much easier way to do it. But nevertheless, you've done this before, and what you got was the expression for the step response. Okay, and that expression, I'm going to write it as V0 of t is equal to V0 for infinite times, I'll say at t equals infinity, minus that same V0 at infinite times, t equals infinity, minus V0 at t equals 0 at the start time, and that whole thing times e to the minus t over tau, where tau is our time constant. And again, these are all things that I think you've seen before. And so what I'm going to do is I'm going to assume that our start voltage here, we're going to assume this is 0 volts. And so if I do that, I can then just simplify my equation here and just write this as V0 at t equals infinity times the quantity 1 minus e to the minus t over tau, where let me just point out that the tau, that's equal to 1 over omega t. Okay, so a little bit of math for this simple circuit right here. And let's now do some plots. So let's plot what we expect this response will be. Let's plot this step response. And so that's the equation for it. So if I did that, let me go to the other side here for more room. And so let's just create one big plot here. Several plots along this line is what I'm going to do. And so for my first plot, that's time. I'll have a second plot here. Oops. How did that happen? And I'm going to want one more plot out of this. I'm not telling you what plots just yet. Okay, so for the first plot, let's just plot my input voltage, VI. And let's take a case where at time t equals 0. So that's 0 time right there. I'm just going to have my step response, my step input occur right at t equals 0. So let's have my step input do this. Let's take it up to this voltage, which I'll call V. But that's my input. At 0 time, I've got nothing. And time below 0 time, I've got nothing. And then suddenly it goes up to voltage V. That's what I'm putting into the input of this op amp on the left. And so what I just derived here is that the output should look like this. It should start at 0, because at t equals 0, that's 1. But as t goes up, it should start rising. And so I think you've seen what this looks like before. My output then is going to look something like this. Right? It's going to go up in sort of that exponential fashion where it goes up to V. Let me be more consistent about... Oops. Yikes. About where I put that V. I want to put it in the same place as my other V there. So that's about there. Okay, so this really does this. Right, that does sort of an exponential motion up to that. Okay, now let's do something a bit different here. Let's stick in a different input to this. And this is where I talk about slew rate and exactly what it is. So let's go green now. And let me put a bigger input in. So let me say that I have a new input. I'll make this a dotted green line. And let's have it go all the way up to what I'll call V prime. Okay, if it goes all the way up to V prime, then that's going to be my new input. And so here I want to plot what happens when I go all the way to V prime. So this is the V prime response here. It's going to be nothing as I get in there. And so what I expect for this response is going to be a similar exponential type response. I'm going to expect it to go up like the dotted line that I'm showing here. Right? I would expect it to do that. This is the expected response when I have this much larger step input signal to this circuit. But in reality, and something you're going to be able to measure in lab at some point. Sorry about that. Forgot to shut off my ringer. Hopefully that person does not call again. But anyway, what you actually get is this. A straight line coming up. And then it hits this point, and then it goes flat. Okay, what's happening here is we're getting a linear increase caused by internal limitations of the op-amp circuit that limit the output current. I'll say that limit the maximum output current the op-amp can source. Okay? And so that linear increase is called slewing. So anytime you hook up an op-amp circuit and you put in a signal that causes this, you expect maybe a sinusoid, or you expect this step response here, and instead it does this, that's slewing. And that's called, and so what an op-amp has is what's called a slew rate. The slew rate, so I'm going to define it right now, is the maximum rate of change of that output voltage. So it's how fast that slope can go up. It's really the slope of that straight line that I've got there. Let me just say the maximum rate of change of the output voltage that's called the slew rate. And that's equal, well, it's often also abbreviated SR, and that's equal to the derivative dV0 over dt, the maximum dV0 dt of that op-amp can source, and that's going to be in units of volts per microsecond, is usually the units that people will use for that. Okay? So let me show you another example. So I'm showing one example here where I really expected to have this curved output, and I'm getting not a curved output, but a straight line. I could show you another example that you'll see more of probably, maybe in this class, where I'm trying to output a sinusoid. But I don't quite get that sinusoid. In other words, if this is my output voltage that I want to see, and that's time, if this is the sinusoid that I wanted to see, something like that, then instead of seeing this sinusoid, I see this. See a straight line that goes up until it hits that point of the sinusoid, and then it starts coming down with the sinusoid, but it can't follow the sinusoid. So it does that, and my sinusoid is not drawn very well, so see if I could draw a better sinusoid to make this look the way that it really looks. All right, so then this red thing will follow sort of like that. Sinusoid's not drawn very well, but you turn the sinusoid into a triangle wave, basically. Let me at least try to draw this correctly here, the way that it's supposed to look. Yeah, this should go down a little more like that, and then that should intersect like that, sort of. And this one is going down a little too. So you have something like this. You basically turn a sinusoid into a triangle wave. And the reason why we're doing this, and so that's happening because of the slew rate. So I'll say the slew rate turns the sinusoid into a triangle wave. And the reason for that is that when the sinusoid starts out here, so you're looking down here, say at this point right here, that's the highest slope of the sinusoid. Right, this is where I've got a large slope in that output. And that slope is equal to dV0 dt. And in this picture that I'm drawing, that's bigger than the slew rate. Okay? But in a sinusoid, of course, as that sinusoid goes up, the slope gets smaller and smaller. Whoops. Until I hit this point right here, right at the peak of this sinusoid, the slope, that equals 0. Right? And then the sinusoid comes down here. The slope is increasing and increasing. But at this point, once it hits that sinusoid, it now tries to determine whether it can actually follow that sinusoid. And in this case, it follows for a little bit, but then the sinusoid slope increases again as it gets closer to zero amplitude, and you can no longer follow, and so you end up with this triangle wave coming out there. That's all a consequence of the fact that the op-amp cannot source enough current to follow that sinusoid. And this is a real thing that happens with op-amps. And so one of the non-idealities that we specify with op-amps is the slew rate. Okay, so I see a question there that Kieran answered there. We're out of time, though. And so I've pretty much told you what slew rate is, and you should have enough really to do all the problems on your problem set right now. There's one more thing that I'll define with slew rate next time, which is the full power bandwidth. But you should have enough now to do your entire homework here. So I guess I will see you on Wednesday then.